Okay. So yesterday we saw the construction of a bipolar junction transistor, and we saw the cross section and the terminal diagrams. Okay, so what we'll do today? So we'll try to derive the current of a bipolar transistor. So as we discussed earlier, so we'll first concentrate on a forward active mode of operation. And common emitter configuration. Uh, for the common emitter configuration and forward active mode of operation. So for the forward active mode of operation, your emitter base junction is forward biased and collector base junction is reverse biased. So if you want to forward bias the emitter base junction, since this is common emitter configuration, your emitter is, let's say we'll put emitter to ground. We are not applying any voltage there. This is put to ground. So I means we'll give some DC bias, DC voltage to base and some DC voltage to collector. So to forward bias, your DC voltage VB needs to be positive because your PN junction needs to be forward biased, right? So this uh, junction here needs to be forward biased. So your VB is more than is around. So let me write down. So your VB will be around zero point 0.6, 0.7 volt, right? It should be sufficiently forward biased. That means this VB, since E is common, so I could write this as VBE, right? So VBE is 0.6, 0.7 volt. This means that this emitter base junction is sufficiently forward biased. Okay. Now the collector base junction needs to reverse bias. So I will apply VC. So VC will be more than VB because I need this junction to be for reverse bias. So VC is more than VB. So I'll just write down here VCE is more than VBE. Right, so I'll apply some voltage to collector where BC is greater than VB, right? So if I do that, then your emitter base junction is forward bias, collector base junction is reverse bias, and transistor is operating in the forward active mode of operation. Okay, so let's see what happens, right? So when in the forward active mode of operation. So uh, so I have VB and VC, and I know that VC is greater than VB, and VB is around 0.6 to 0.7 volt, right? Okay, so this is N type. So your collector and emitter base. So emitter is, this is NPN transistor. So emitter is N type emitter, P type base, and N type collector here, right? So let me. Okay. So since emitter base junction is forward biased, so I have a depletion region here. So basically each junction has a depletion region. So let's say I'll just note down, means just write on the depletion region here. So so for our operation, means for derivation of the equation, let's put this as 0. The emitter base junction is at 0. Then this will be at TB, the thickness of the base, and this is at minus TE, right? And this will be TB plus TC. Right? So TB is the thickness of the base region, and TC is the thickness of the collector region, and TE is the thickness of the emitter region. And so this junction is forward biased. So I have so I'll have depletion region here. So let's say this part here. So this is, let's say, dB1, right? So this is the depletion. Sorry, this is plus, right? Right. So dB1 is the width of the depletion region in the base side, and this is minus DE1. Or DE, because I have only one junction here. So minus DE, that means your depletion width, the depletion width in the emitter side, right? DE. And similarly, I'll here also, because this junction is forward bias, so I'll have a depletion region which is thicker, right? And So because when you reverse bias it, so your depletion width increases, right? So your collector base junction depletion width will be more than emitter base junction depletion width. Um, so so this is my depletion width, and let's say this is here. Uh, so TB minus DB2. So DB2 is the depletion width towards base in the base side, and this is TB plus DC, right? Okay. So I have neutral region. So this, let's say this neutral region. So this neutral region here, right? This is TB dash, right? And TB dash, the thickness of the base neutral region is nothing but TB minus DB1 minus DB2. Okay. But keep in mind, see this dB1, I mean dB1 will be very low because this is for bias, right? So dB1, this dB1 here, because this junction is for bias, this is very low, right? So compared to TB, your dB1 is much lower, right? So you could also calculate. So dB1 is much lower than TB, right? Because this is far biased junction, and dB2 is also lower than TB, but dB1 is anyway uh, uh, lower than dB2, because you see this junction is far biased, by sufficiently far biased, right? So uh, so means your dB1 will be much lower than dB2. Okay, fine. So now, so I have n region emitter. So this is majority carriers are electrons here. So I have electrons in the n side. So when I forward bias this junction, so the electrons are injected, right? So electrons are injected, right? So your electrons will be injected from emitter to a base, right? So these electrons, so the concentration of electrons at this point. Okay, we'll talk about that later. So the electrons are injected, and then this electron, so we have excess minority carriers, so excess electrons at this junction here, right? And these electrons, because I have a concentration gradient, because I have lot of electrons at plus dB1, right? And then and so these electrons will diffuse, right? So these electrons will diffuse, right? So electrons will diffuse. So during the diffusion, so they will go from dB1 to TB minus dB2, right? So they will go from this point to this point, and they will diffuse from this dB1 to TB minus dB2. They will diffuse, right? So during this diffusion, so there is a possibility of recombination. So some of the electrons here will recombine. So the moment the electrons recombine, that means some holes are also uh, so because the electrons will recombine with the majority holes in the base, right? So that means the hole also depleted, because the moment recombination happens, some holes are neutralized. So if some holes are neutralized, the holes are supplied by this battery, right? So I have, so this is my electron, and similarly, since some electrons are recombined, so I will have um, some holes will go, right? So basically, I'll have some holes. I mean, some. Okay, okay. So similarly, uh, the moment, right? So if you look at the electric field at the junction, right? So I have an electric field. So I told you yesterday. So there is the electric fields are always N to P. So I have a electric field in this, which is, let's say, epsilon electric field 1, and there is or I could write electric field at base emitter junction, and there is electric field into is base collector junction, right? So which electric field is higher? Because your base collector junction is reverse biased, right? Base emitter junction is forward biased, right? The voltage, what is the voltage drop across base emitter junction? Voltage drop across the base emitter junction is VBI, right? VBI minus applied voltage, VBI minus VBE. So voltage drop here will be VBI minus VBE, right? But the voltage drop in this junction is VBI plus VCB, right? So because this junction is reverse biased, so I have a higher amount of voltage drop in the collector, base collector junction than base emitter junction, right? So the electric field, if you calculate the electric field, you could easily calculate the electric field if you know the doping. So if you calculate the electric field, your EBC, right? So your EBC is higher than EBE. So you have a very high electric field at the base collector junction, right? So the moment the electrons reach, because they will diffuse from dB1 to TB minus dB2, and some of these electrons are recombined. So I have a whole flow from a base, right? Um, some of the electrons will reach here. The moment they reach, because there is a very high electric field EBC, so these electrons will pulled, right? The whatever electrons will reach at the edge of the depletion region at this point here, right? So these electrons will be pulled to the collector, because there is electric field EBC, which actually aid electrons to be means to be pulled, right? So then these electrons will reach um, collector, right? And right, okay. Similarly, so since you are forward biasing this junction, the holes are injected from base to emitter, right? And these holes will diffuse, right? Right. So because if you look at this junction here also, so I have excess holes at this junction at this point minus DE, then there is a concentration gradient and the holes will diffuse, and these holes will diffuse and they will recombine, as I told you during the PN junction also, because here I am taking the contact, and this at the surface all the excess holes will be recombined, right? So they diffuse, there is a possibility of recombination, the holes will recombine also in the emitter region, and the rest of the holes will recombine at the surface. Okay, so okay, and also, so if you look at the base emitter junction, we have electron current from emitter to base, electron injection from emitter to base. So there is a current. So I could have a IEN. So this here, because there is a electron current, because uh, so emitter will have a component uh, of electron current IEN, right? Similarly, there is a hole diffusion. So this has also a component IEP, right? Let me write down, do it by red. So I have a IN, I'll have a IEP, right? Okay. So there is also, because some of the electrons are collected by the collector. So there is so some of the, so this will be ICN, because uh, this some of the electrons are recombined and rest arrives at the collector. So rest are collected by the collector. So there is a current ICN here, right? Okay. So also, if you look at this junction here, right? If you look at this reverse biased junction, right? So there is a very high electric field across this junction, EBC, right? So I have minority carrier. I have minority carrier holes here, right? Because this is N type. So I have a minority carrier holes. So these minority, so in the reverse bias junction, you have minority carrier which flows from N to P by drift, right? So this will give you something IC0, right? So there is holes flowing from collector to base, and that is nothing but reverse current, right? IC0. Okay. So there is a whole flow, and this flow here, this is the recombination current. So this is IBR, right? Because if you see, as some holes, some electrons are recombined with the holes, there is a hole gradient, and you have hole supply from the base, right? So basically, this IBR, this is the recombination current, right? Right? If there is no recombination in the base, then IBR will be zero, right? So these are all um, components of the current, right? So I have IEN, IEP, ICN, IC0, and IBR. Right? Okay. So are there any questions here?
Sir, this current ICN, it is because of the drift of the minority carriers in the base towards the
No, minority carriers do not drift because there is no electric field. They will diffuse, right? No. Minority. Okay. Yeah. So this IC0 is my minority carriers drifting, right? But here, if you see, I have in this region, right? So okay, this is a good point. So I can also have minority carrier electrons in the base drifting towards, right. So this has a okay, I could write down this has a p component and there is a n component also, right. So I have minority carrier holes in the base and they could drift because of this electric field EBC, right. But this ICN is because the electrons are injected from emitter to base and they're diffusing in the base. They're reaching the base collector junction. The moment they reach base collector junction, because I have a high electric field, they are just pulled, right. So this ICN is not minority. This N is not a minority carriers present there because this is somehow you could think of these electrons are injected from the emitter. They are not present in the base, right? Earlier, right? Huh. Is it clear, Monica?
yes, sir. Yes, sir.
Okay. So so now, so these are all the current components, right? And um, if you see now, you see, okay, let me copy this. Uh, all right. So here, if you see, um, so if I look at the terminal current, right? So this is current inside your transistor, your bipolar transistor. But if you look at the terminal current, so your emitter current will come out because if you see your IN, IP are from base to emitter, the direction like that, right? So I could write IE is nothing but your emitter current is nothing but IEN plus IEP, right? Emitter current because of electrons and emitter current because of holes, right? Similarly, if you look at IC also your current is something like this because electrons are collected, right? So the current will be inside. So your IC you could write down, right, your ICN plus IC0 component, right. So this is the reverse current, ICN plus IC0. Okay. Similarly, if you look at IB, right, so IB, if you look this terminal here, so you see um, so um, so if you solve the KCL, right, so IB will be IP, right, plus IBR minus ICO, right. So um, okay. um, so basically your ICO is very low. So we could write down this as approximately at ICN, and this approximately nothing but IP plus IBR, right? R combination current, right? So if you see these equations here, so your emitter current is because of hole and hole current, the electron injected from emitter to base and holes injected from base to emitter. Your IC is mostly because of how much electrons are collected after recombination, right? and your base current is nothing but how much, because if you think from the diode point of view, your holes are injected from base to emitter, so this component will come in the base current plus the recombination current, right? Okay, so then so if you understand this, so there are a couple of things I just want to discuss the terminology. So we'll come back to the current later, means how to derive the current equation. So there is this terminology alpha, beta, right? So this alpha, this is called common base current gain. Common base current gain. So common base current gain means when base is common, right? So when base is common, so basically, as I told you yesterday, when base is common, then you will give your input to the emitter and you take the output from the collector. So that means this common base current gain will be nothing but output current by input current, which is IC by IE, right? And similarly, there is a terminology called beta. This is common emitter current gain. So when your transistor is operating in the common emitter configuration, so your output current is IC, your input current is IB, right? This is IC by IB, right? So this is common base current gain and common emitter current gain. So if I want to, because you see, as I told you yesterday, right? So if you think from a bipolar junction transistor here, right? So your base current is going in. Let's say this is NPN transistor. Your base current is going in. Your emitter current is going out, and your collector current is coming in, right? So because um, this is your control terminal, right? So this is your control terminal, right? So you do not want your IB to be very high because your control part should not dissipate a lot of power. So your IB should be very low, and your input means whatever is the output current, they should be constant, right? Basically, uh, IC should be equal to IE, right? So that's the reason, because your IB, so basically you just keep in mind your base current IB should be as low as possible for a better transistor, and your IC should be equal to IE, right? So your common base current gain ideally should be 1, and your beta, which is common emitter current gain, should be as high as possible, because I do not want any IB, I do not want any power dissipation in the control part, right? Okay, so if I go a little bit more, let's say alpha equal to IC by IE, right? So I mean, I don't want to derive this, but you could also write down, because if you see here, if you look at this terminology also, your IE, um, IE equal to IC plus IB, right? So you could write down, right? So you could write down. So this has IC, I means you could write down this IC by IC plus IB, right? So I could do that is 1 plus or IC by IB, I divide by IB, so this will be IC by IB plus 1. So these things you know, right? Means I don't have to do this, right? So this is the relation between alpha and beta. So alpha equal to beta by beta plus 1, right? Anyway, okay. Then, but if you look at your alpha, I could write down, um, so let me write down in another form. Alpha is IC by IE. So I could also write down by IC divided by ICN, ICN divided by IEN, IEN divided by IE, right? So let me write down in this. So this is the same thing, right? Alpha IC by ICN, right? ICN by IEN and IEN by IE, right? So these terms has different meaning. So uh, you know, so this we call it IC by ICN. So if you look at IC by ICN, so uh, your IC. So if you look at your IC here, right? Let's look at IC, this part here, right? So IC is ICN plus ICO, right? ICO is your reverse saturation current, and that is in that junction. But here I told, okay, this reverse bias is not very strong, so that ICO can be neglected. But as we discussed in the PN junction, right? If you go on increasing the reverse bias across the collector base junction, at some point of time your ICO will be very high, because there will be avalanche or there will be Zener tunneling, right? So there will be avalanche multiplication or Zener tunneling, right? So in that case, your your ICN will be means basically your IC will be mostly dominated by ICO, right? And your ICO by ICN will nothing but the multiplication factor, right? So so this is multiplication factor, but in normal case, in the operation means when you're operating bipolar junction transistor in normal operation, right? So here IC is mostly equal to ICN, so this IC by ICN is equal to 1. But if you go on increasing the reverse bias, at some point of time your IC by ICN will be very high, and this is the multiplication factor, right? ICN by IEN, right? So basically what is ICN by IEN? So I am injecting electrons, right? That is IN, right? IN amount of electrons I have injected from emitter to base. ICN number of electrons I have collected, right? So what means, I have injected some electrons. Electrons are traveling across the base. Then ICN amount of electrons are collected. So that tells me the collection efficiency, and we call it the transport factor, right? Base transport factor, right? Because the IN amount of electrons are injected, but ICN is collected, right? So what is the transport factor? Means how much means during the transport, how much electrons have leaked, right? How much electrons have recombined, the rest of it. So this is my transport factor, and I call it mostly, this is done by by factor alpha t, right? So this is the transport factor, right? What is IEN by IE? So what is important? See, if you look from an NPN by NPN transistor, so the current is because of electrons, because we are not, see your current, because electrons are injected, electrons are collected. IC and IE is mostly by electrons, right? But if you look at IE has two components, IN plus IP. But IN is the most important component out of this total IE, right? Total emitter current, right? So this just ratio tells you what is the useful component out of the total emitter current, right? IEN by IE, because I don't care about IP. IP is not contributing anything to collector, right? So uh, so this is called emitter injection efficiency, that is gamma. So injection efficiency is out of total emitter current, how much electrons are injected. That means if my total current is IE, right, and IN is the injection current, so what is the percentage of injection current total of IE, right? That is the emitter injection efficiency. Emitter injection efficiency. This is emitter injection efficiency, and this is base transport factor. They are very important parameters, right? Base transport factor, because, and this is your multiplication, right? But in the normal case, as I told you, this M will be 1. But if you go on increasing the reverse bias collector base junction, at some point your IC by ICN will be very high, right? And your alpha will be huge, right? Because IC just explodes, right? That means exponential increases, so alpha will be very high. Right? So now your alpha I could write down as M multiplication, your base transport factor, and in emitter injection efficiency gamma, right? So and in the most case you will see this is written as alpha t into gamma because normal operation m is almost 1 because means we have not n multiplication. We are not applying very high reverse bias across the collector base junction. Okay, so yeah, so this is alpha. So basically, if we want our alpha to be 1, right? So because I want my IC to be equal to IE, so alpha to be 1, that means I have to improve the gamma in injection efficiency, and I have to improve alpha t, right? Right. So if I write down what is alpha t is ICN by IN, and this is IN by IN plus IP, right? If I want to improve this part, right? Let's say I want to improve this IN by IN plus IP. What I have to do, right? I have to make sure that this IP component is very low, right? Then IN by IN plus IP could be improved, right? Right. And similarly, if I look at this part, ICN by IEN here. So if I want to improve this, I want to make sure that ICN is very close to IEN. That means I have to reduce the recombination component, basic recombination component, right? So to improve alpha, so I have to make sure that IP to improve alpha. So your IP should be close to 0 and your base recombination current be equal to 0, right? So if IP equal to 0 and IB are equal to 0, then your alpha will be 1. That means if this is happened, somehow you manage to do it, then your alpha will be 1 and your beta will be very infinite, right? Beta will be infinite, right? That means you have a very high beta transistor, right? High beta transistor means if you look, means the significance of beta is IC by IB, right? So your control, that means you are getting very high collector current, without this IB being very less IB, right? Because you are not dissipating anything. This is something like you are doing work very efficiently, right? And yeah. Okay, so this is the theory part. Then because we have to, as a device engineer, or I have to design the device so that your IP should be equal to 0 and IBR should equal to 0, right? How to do that, right? So for that, let's derive the current, because once you derive the current, we understand from where the current is coming. Then we could see how to how to optimize that, right? Um, so, um, okay, um, let me draw again. So let me draw only the emitter base junction. Yeah, any questions from anybody?
Sir,
Yeah, Monica.
can you please tell how we have got IB here? IB equals to IEP plus IBR minus ICO, like in that diagram you showed. Yes, sir. In
Yeah,
this one.
yeah. You see, IB means you could do the KCL, right? So this is, let's say, terminal. Your IB is going in, right? So this is IBR, and this is IP, and I have ICO coming, right? So if you solve this KCL, right, what will you get?
Yes, sir. Understood.
Yeah, this is just a KCL, right? Just KCL to capture correctly. Okay, so now let's derive the current. So let me, right, let's me focus on the emitter base junction. So this is my emitter part. This is my emitter junction, which is, I'm telling, 0. Then this is my DB1 here, and this is my base junction. This is TB width. Then I have DB2. dB2. And I have here DC and I have here DE, right? And this is 0 and I am applying this is terminal voltage 0 here and I am applying a VBE here, right? Okay. So okay, so we know how to, because we have so this is n type, this is n type, this is p. So I have in the equilibrium condition I have a number of electrons here in the n0 is ni square by nb, right? And number of holes in the equilibrium is b, right? And similarly number of electrons in equilibrium here, this is b side, right? n0b and p0b. Let's say n0e is ne and p0e is ni square by ne. Okay, right. So we have done this derivation earlier, so let me redo it. So you are forward biasing this junction. This junction is forward biased. That means I have electrons injected. So the electrons at this point, so I'll have electrons injected here. So the electrons, number of electrons at dB1 will be the whatever electrons existing before the equilibrium concentration times exponential VB by VT. So let's say VT is KT by Q, right? VT is equal to KT by Q, right? Uh, right. And I have excess. So this is the excess electrons in the at dB1 is Ni square Nb e to the power VBE by VT minus 1. Right? This part we had done. I don't think you have to. I mean, I think you understood. All of you knows that this part, right? Okay. So now, as I told you, so the if the electrons reach this point, so they are pooled, right? So this is something like uh, all the excess carriers here, so they experience a very high velocity, I mean very high electric field, right? So that means they're instantly pulled to the collector side, right? So the equilibrium concentration here, right, if you look at the steady state, right, steady state, because we are thinking of steady state. So in the steady state, the electron concentration here will be ni square by nb all the time, because I have electron higher electron concentration here because of injection, some excess magnetic carriers. They are diffusing, but the moment they reach this edge here, edge of the depletion region in the collector side, so they are just pulled. That means we maintain the steady state. That means the here I have ni square by nb all the time. So your delta ne at dB2 is always 0, right? Because these excess carriers are always pulled, right? So you think, right, we are injecting, the moment they reach collector, they're pulled, right? So they're just evacuated, right? So I am putting some electrons in the base from the emitter. The moment these electrons reach, so they just evaporated, right? So if you look from the steady state, if you think from the steady state point of view, so there is no excess carriers at the collector junction, right? So these are the boundary conditions, right? So then, but I have to then if you write the continuity equation in this side, and so if you take it as a box here, right? So this part here, because I am worried about this part. Sorry, let me put down another, right? So I am now, so if I write the continuity equation, because I am injecting electrons are evacuated, means electrons are pulled, collected, I am injecting, then electrons are flushed out. You could think of flushed out, right? So the moment they reach the collector junction, they are flushed out, right? So, so if I look at this part, if I write the continuity equation, right? So how I'll write the continuity equation? Continuity equation tells you delta n by delta t. So this is I am mostly concentrated about this excess carriers, right? Delta Ne by delta T. This is 1 by Q because there is electron current, delta Jn by delta X, right? Plus Gn minus Rn, right? So what is this? So let's under steady state. Anyway, so I could write down this. So let's say I do not have any generation because I'm not flashing light. So I'll have minus Rn here, right? So this is my right. So what is this Rn? Rn, okay. So Rn is a recombination part, right? But if you see, so for the time being, I mean, our whole goal, as I told you, right? Our whole goal is to make sure that your IBR is very less. The recombination, very less recombination is happening inside the base, right? And in the bipolar transistor design, we took a lot of effort to make sure that the recombination is less. How do you make the recombination less? So you have to make sure that the base part do not have any crystal defects, any defects, and you have to make sure that means we'll come to this point. You will make sure that your base width is very less, that so that there is no time for recombination, right? So, but whatever carrier dynamics happening, right? So electron, I mean, here we are talking about because delta Ne by delta T. This means if you take this closed area in the base, so continuity equation, what does it tell, right? So I'm injecting electrons, and if I look this point, so right, and your something is coming out. So if you look at and generation recombination happening inside that volume, right? But if you see most of this uh, delta Ne by delta T, most of this change in carrier time is mostly coming from injects this part, right? Right. So for the time being, if you look at these two components, right, this and this, right. So let's say this is x1 and this is x2, and a contribution of x1 is very means less than x2, right? I could still keep this and solve this equation, but if I want to have a simpler, because as an engineer, we know how to approximate the things, right? So if I approximate, I know that okay, the recombination is much less than this because the carrier dynamics happening because of recombination is much less than injection, right? So this x1, I could assume, okay, let's say x1 is less than x2, right? If I do that, your equation will become simple. Delta Jn by delta x will be 0. Right? There is just this is a simple equation, and I know delta by del x because this is happening because of Jn is because only because of diffusion. So delta del Ne by del x equal to 0. Right? So then I could write this is dn, right? Q cancelled, del square del Ne by del x square equal to 0. I could easily solve this equation, right? See, the moment I neglected Rn, I have not put it 0. I just make the approximation that x1 is less than x2, right? Right. So then this equation becomes simple. So that means delta square delta Ne by delta x square equal to 0. So I could write delta Nex if I solve it. So this is how the, let's say, A1 and B1. So this is how your carriers means your electrons electron half means with respect to x, right? So delta excess carriers delta Ne x equal to A1 x plus B1. Then I have to put the boundary condition, right? And the boundary condition is I have already have here. I have this boundary condition with me, right? So then if I do that, then my Ni square, okay, let me take it to the next slide so that I'll have space to write down the equation. Right? Okay. So if I just use, then it will be Ni square by Nb exponential Vbe divided by Vt minus 1 is equal to A1 dB1 plus B1. And this will be 0 A1 dB2 plus B1, right? So here I could write down A1 dB1 minus dB2 is Ni square NB e to the power Vb by Bt minus 1, and from here you could find A1. So dB1 minus dB2. What is dB1 minus dB2? So this is nothing but this dB1 minus dB2. This is nothing but neutral region, right? So and we have defined this as TB dash somewhere, right? Yeah, this is something around TB dash, right? That we have defined here, right? Right. So I could put it as minus A1 TB dash equal to Ni square by Nb e to the power Vbe by Vt minus 1. So your A1 is minus Ni square Nb Tb dash e to the power Vbe by Vt minus 1. Right? This is your first constant A1. Right? And you know, right? If you from this equation also you know that your B1 equal to minus A1 minus A1 dB2, right? So now if I put it, right, your delta NEX A1x minus A1x minus B1, which is A1 dB2, A1x plus B1. So this will be A1 times x minus dB2, and A1 is this one, minus Ni square B dB dash e to the power Vb by Vt minus 1 x minus. Okay, so this is my delta NEX, right? So now my current equal to Q dN delta NEX by dx, because this is diffusion current. So if I do this Q times dN, so it will be minus Q times dN times Ni square divided by NB TB dash e to the power Vb by Vt minus 1, and this will be 1, right? So your current, and if I want to write this in terms of IEN, right, because then you have to multiply your Jn by the area, and I told that active area is your AE, so I have to multiply by Q times emitter area dn Ni square divided by NBTB dash e to the power Vbe by Vt minus 1. So this is my IEN, right? If all of you, we just derived, right? So don't go by this negative sign. Negative sign just tells you the direction of current, right? So because your x is increasing from left to right, but you have a negative sign that the current is flowing from right to left, right? So this is just the negative sign, you just have to take care of. This just tells you the direction of current, right? Okay, so once we have done this IEN, right? So then similarly, I mean, this is my IEN, right? So any questions here from anybody, or you understood how to derive? So we have done this derivation for the PN junction, right? So we have just used the same derivation here, right? Okay. Now, similarly, I could also derive for the IEP, right? Because if I take this again here, copy, IP is the whole, so IP will be whole current, right? So because the holes are injected from base to emitter, right? So in that case, there is excess hole current. So my delta P E, because minority carriers, excess minority carriers at minus DE is Ni square divided by Ne e to the power VBE by VT minus 1, right? So scalars will be this one, right? Right? And your del PE at TE, the emitter thickness, is 0 because as I told, these holes anyway they will recombine at this because there is a metal junction surface recombination velocity will be very high there, right? And they so this then again um, so again we have to write this equation, right? So delta, so if you write down the recombinant means your continuity equation, right? So basically now we are mostly focusing on this part here, right? So we are focusing on this box here, right? Right. So this is minus 1 by q because this is whole current plus gp minus rp, right? So gp is not there, no generation, right? And in the steady state, I could write 0 equal to minus 1 by q del jp by del x. Again, right? So I am assuming that this component um, is less than that. So um, let's say this is x1, this is x2. Again, I am assuming that x1 is less than x2, right? So the dynamics is mostly happening because of injected holes, right? The combination that is something because the holes are recombined, but that is less, right? Assuming that is less compared to the injected holes. So you have this equation, right? 0 equal to minus 1 by q del jp by del x. And your jp is nothing but q dp delta pe by del x. So in that case, I have my equation will be del square pe by del x square equal to 0, right? And I know delta pex will be a2x plus b2. This is a very simple equation to solve. So see the advantage I just mentioned to advantage, because if you put this rp, then we'll have an exponential term here, right? Because rp will be if you take rp here, right? Rp will be delta pe by tau p, right? And if you solve this, then this will be this equation here. It will not be 0. It will be delta pe by tau p, right? If you solve this, there is an exponential term. To handle the exponential term in the equation is always difficult. So I have made this approximation, assuming that this x1 component is less than x2. I could always put this to 0, assuming that delta p by tau p is very less, right? So that's the my equation becomes linear equation, which is very easy to solve, right, by hand, right? But if you tell me, okay, this is approximation, if I want to derive exact equation, then I cannot really neglect this recombination term, right? All right. So now, if this is the case, then I know the boundary condition now, right? Boundary condition. So you could solve, right? So then you could easily find. Um, so let me. So your JP. So you do this math, right? So your JP will be Ni square dp divided by any T dash, right? E to the power VB by VT minus 1. What is T dash? T dash is this length, right? T dash, and T dash is nothing but TE minus DE. So TE minus DE, as I told you earlier also, right? So this junction is forward biased, right? So emitter base junction is forward biased. So DE is very less compared to the emitter thickness, right? So your TE dash will be equal to TE. That is a fair assumption, right? You could even calculate, right? I mean, so you have equations. You could calculate what is the thickness, what is this DE, right? Anyway, so this is my JP. Then if I want to find IEP, because I'm interested in the current, so this JP is the current density. Then I have to multiply, right? Ni square times AE. Oh, current, right? So this is, so I forgot to chart somewhere, right? So this Q. Ni square AE dP by NE T dash e to the power VP by VT minus 1. Okay, so now, I mean, so you could do it by yourself, right? So I just skipped the derivation. So we have done the derivation for IEN. So you have to exactly follow the same derivation for IP. So there is no, and you'll get this, right? IP is Q Ni square AE dP by NET dash, right? It will dV by VT. So in the last class yesterday, so I focused on emitter area, right? So that's the reason I focused on emitter area, right? So when you find the, see your, if you look at emitter based junction, so let me go to the our earlier diagram, somewhere here in the beginning, right? See here, right? So yeah, so okay, let me. So you see your emitter base junction is this one, right? Emitter base junction, right? And this is my emitter area looking from the top. But if you look at collector base junction, but if you look at extrinsic part plus intrinsic part, this is this, right? But I'm not, so then uh, I'm not interested in that area, right? So basically the injection, because this BJT, the current is because electrons are injected from emitter to base. That's why this name is called emitter, right? This emits electrons, right? So whole means current is because of this injection from the emitter base junction. So I means the current will increase if the area of the emitter base junction is increasing, and emitter base junction area is nothing but AE. So that's why you have to always worry about this AE, and this part that I draw in the layout also, this AE part, which is WE times LE, is very important, right? So your current will scale with this area, right? If you increase this area, your current will increase, right? Which we have derived also, right? So here. Okay, so what you have done? Um, we have done IEN, we have done IEP, but what I have to find out? I have also, I have to find out ICN, I have to find out IBR. Then I could find out alpha, beta, gamma, all those things, right? And I could find how, means I could now, after I find this equation, then I could see how to design to reduce these components, right? Okay, so how to find IBR, right? So IBR is the base recombination time. Sorry, base recombination current, right? And or recombination. So if I again go to the emitter base function, base mostly. So I have my emitter, I have my collector, right? So let's say this is emitter. Okay, this is my emitter, this is base, this is collector, and these are the depletion width, and this is my 0, this is TB, this is my TB dash, right? So if you look at the equation here, so if you look at the excess minority carriers, right? So I have excess minority carriers. So if I plot the excess minority carriers from this side to this side here, so this will follow a straight line, because if you look at the equation, right? If you look at the equation, delta NEX right? Yeah, so delta NEX is A1X plus B1, right? So A1X plus B1 is nothing but we'll have something like this, is a straight line, right? So delta N, and what is this point here? This point is uh, this is delta NEX, and this is X, and this is my 0. Sorry, this is dB1, this is dB minus dB2. Okay, so here I have Ni square by Nb e to the power Vbe by Vt minus 1, right? Excess carriers, right? And here I have 0, right? Right? Okay, so if I want to see in steady state how many excess carriers are there, right? If I want to see okay, how many excess carriers there, so I have to take the area under this curve, right? So the area under this curve is nothing but total excess carriers, right? And in this case, total carrier excess carriers in the base, right? At the some point total charge, right? So this is the total charge in the base, right? So excess charge in the base, right? Delta QB. And this is because of electrons. So let's say let's put is QNB or BN, right? Whatever, right? BN will be better, right? This is total excess carriers on the base, and this is because of electrons. So let's put N, right? So how do you find delta QBN? This is the area under this curve, and the area under this curve is half, means you know the triangle, so half of the base into height. So this will be half. Base is TB dash, right? And the height is Ni square by NB times e to the power Bbe by Bt minus 1, and total charge, so I have to multiply by Q, right? Because this is the electrons, excess electrons into charge of electron is Q, so this will be, so basically total charge is Q Ni square Tb dash divided by 2 Nb e to the power Vb by Vt minus 1. So this is the excess charge, right? So this excess charge is moving, right? So basically means in other way, you could think, right? So in steady state, this is this delta Q, this is the excess carriers in the base, and current is nothing but the these excess carriers are collected because you are injecting and these excess carriers are collected at the collector, right? So you could think of a charge packet, right? This is, you think of this as a charge packet, and I have injecting a charge packet here, and this charge packet is collected, right? So how do you define IEN? Because this current we're talking about IEN, right? So how do you define this IEN? So you could also write IEN equal to this BN, right? And a time, right? Time, right? Because your, see, what is your current? Current is charge collected in a particular at a particular time, in a particular time, right? And this is this time is called the transit time, because transit time, you could define this transit time here, TT, or TT, how much time this charge packet takes to travel from emitter base junction to collector base junction. That is the transit time. Transit time across base, right? This is the transit time across base, right? So I could also write this current. The current will depend on this delta QBN by this transit time, right? Charge by time equal to current, right? So if I do that, then I could find also current equation. PB dash 2NB and TT the transit time, right? So TT e to the power Vb by Vt minus 1, right? So I could write also current in this form, right? If I know the excess charge, then I could write in this form. And this current I could equate also with the current that we have derived, which is IN, which is QAE. Okay, current means I have to multiply AE also, right? I could not skip AE, right? Because I have to multiply, right? Total charge, right? This is AE. Q Ni square AE and dn and B TB dash e to the power dB by VT. So this we had earlier derived. This we have earlier derived, and this we have derived this now, right? But IN, I mean, these two currents are equal, right? So I could find out the I could find out. So basically, if both of them are equal, then so here I could write down TB. Let me copy this. Right. So if these two are equal, then if I do some, then I could. So I could this Q jaga N square AE, sorry, AE and B. So I could write down as TB dash by 2 TT equal to DN or TB dash is TB dash. So TT from here is equal to TB dash square by 2dn. So this is the equation for the transit time. So this is the transit time across base, right? How much time? Actually, this will give you how much time the charge actually spending in the base, right? So TB dash square by 2dn, right? So this is means this has a physical significance. Also, you could see the transit time will be less also if TB dash is less, right? TB dash is the thickness of the base, right? If the thickness of the base is less, it will spend less time. It will be easily means it could be for means transit time will be less, right? TB dash less means transit time less. Then is the diffusion coefficient. If diffusion coefficient is higher, that means it's diffusing faster. So your TT will also be less, right? So your transit time is TB dash square by 2dn, and see your if you know you could calculate always the transit time, right? Because if you know the doping, right? So there are graphs available. You know the base doping, right? So base doping, if you know base doping, right, then you could find dn from this is you could easily find because there are graphs available. So if you know NB, then you could know dn. If you know dn and you know TB dash, you could calculate the transit time, right? You could calculate the transit time very easily. Okay, so this is the transit time. But again, if I want to find the IRB, right, I base recombination. So recombination, if there is some excess charge, this is QBN. This is the total charge I have, delta QBN times AE, right? Or let's say AE is already inside. So by tau n, right? So your IBR recombination is depends on this minority carrier lifetime, this tau n, right? Right, and the excess carriers, right? So this is my IBR also, right? So here, yeah, I could multiply by AE also here because let's say, okay, so this is the total charge. So this is gives you total charge, right? So the if Q, this will give you the total charge Q delta QBN times AE, and this total charge by the minority carrier lifetime is your current, right? So here you see, you know,
Sir,
yeah, listen.
Here, why we are multiplying with AE means we are trying to calculate the base recombination current. So area of base should be multiplied.
Again, area of the base is, what is area of the base? Area of the base nahi na. So okay, so let me do that, right. Okay, हमने तो ये calculate कर दिया ना, right? So basically you see this is my 0, this is TB, this is my base, right? Right? And we had calculated the area under this curve, right? Basically we have calculated the area under this part, right? But what is inside this screen, right? So I have this, right? So uh, inside that screen, right? So you have to also think of, right, this part, right. So we have already done this area under this curve, right. But if you want to find a total charge, right, then you have to basically you think, right. So there is base, right. So इसका तो एरिया लेना पड़ेगा.
Okay, sir.
No, if you don't get it, don't tell okay, right. Did you get that, or all of you? It's a question to all of you. Hmm? Is it
Yes,
okay
sir.
for all of you? What about Om, Monica, Sarda, Aditya, Shruti?
Yes, sir. Clear.
Nishant, you still have doubt, or you this? Don't tell yes, right? If you
सर
still
नहीं
don't
सर यहाँ पे
understand, ask
सर
questions, right?
नहीं सर यहाँ पे इमीटर एरिया क्यों लिया सर वो क्लियर नहीं हो पाया.
Okay, ठीक है. तो एक काम करते हैं. Let's say I'll do a 3D plot. I'm not very good in 3D. So let's say this is my base, right?
Yes sir.
Right. This is my base, right? So the AE is this area, right?
Yes sir.
This is my AE, right? And then I had this. How will I draw it to make it clear? So let me try. Um, did you get my thing? So basically, your charge is concentration. Charge is going like this, right?
Yes sir. Got it.
It is clear.
Yes sir. It is clear.
Okay. Now, if you take the total volume of this region, right?
Yes
So
sir.
what I have done, we have taken this area of this triangle, then multiply by AE, right?
Okay. Okay.
Right, and this into this part, right? Huh.
Yes yes sir.
So
Got
total
it.
charge मिल जाएगा ना. हाँ.
Got it. Got it.
Okay. All right. So इसलिए हमको हम इधर ए भी मल्टीप्लाई किया ना. I multiplied the e here also, right? This part here.
Yes sir. Got it.
Okay. Then this I know. I have delta QBN. So QBN तो मैंने find किया था पहले. Right, QNI square TB dash by 2NB. QNI square TB dash by 2NB. +1 इसमें आ जाएगा AE by tau n. So your IBR is nothing but QNI square AE TB dash by 2NB tau n e to the power VBE by VT minus 1. So this is your recombination current. This is how you see. This is the easiest way to find recombination current, because what you have done is, if you know the tau n, so tau n is the minority carrier lifetime. So minority carrier lifetime will depend on the defects inside that base region, right? So let's say your base region is highly defective. There are a lot of crystal defects, other defects. Then your tau n will be very low, right? If tau n is very low, your recombination current will increase, because there will be more recombination, right? Here also you could see, if the TB dash, the thickness of the base region, if that is low, that means your either your charge is low, and also the moment your total number of excess carriers are low. So basically, recombination, we have discussed earlier, right? Recombination is delta n by tau n, right? How many excess carriers are available? So recombination will only happen if there are excess carriers, right? If there are no excess carriers, recombination will not there, because excess carrier means I have a non-equilibrium condition, right? So think of, if I have a semiconductor, I am flashing light, I am generating delta n, delta p here. In conduction band I have delta n, and valence band I have delta p. That means these are the excess carriers, right? Now, if you remove that light, so these are excess carriers, and they'll recombine. And the recombination will depend on this tau n and tau p. This is the lifetime of the carrier, right? And your recombination R is nothing but delta n by tau n, right? If your tau n is very low, that means it's slowly recombining, because there are not much defects. So you will see your R will be very right, low, right? If tau n is high, your R is high. If tau n is low, then your recombination rate will be right. So in this case, in our case here, I am injecting excess carriers to the base, right? Right, and these carriers are recombining, right? So there is this carriers of this. So that's the reason I have put delta QBN, this total charge, by tau n, right? And if you derive, it will be like this, right? So this is my recombination current. Okay, now we have done almost all. So let me write down one by one. I have IEN. Okay, let me write down. IEN is Q Ni square AE dn divided by NB TB dash e to the power BP PT minus 1. This is my IEN. IP Q Ni square AE dp n e te IBR Q Ni square AE TB dash 2 NP tau n So now I have IN, IP, IBR, right? And if I want to find my emitter injection efficiency, or let's do one by one. So emitter injection efficiency eta equal to IEN divided by IN plus IP, right? So so this is not the useful component, right? So so basically, injection efficiency, total current is IE, and how much percentage of IE is IEN, right? So that is the injection efficiency, right? Because this is the useless component, right? Because this is not coming in collector current, but this is unnecessarily increasing IE. This is also increasing IB, base current, right? So so I want my IP should be as low as possible. Should be as low as possible, right? Because as a device designer, if you want to make a very good transistor, then IP should be low. And how will you make IP low? If you go to the let's go to the equation here, right? IP ka equation mein jao, and you see here if I want to IP low, क्या कर सकते हैं हम, right? एक तो there are couple of things, right? Either you could increase the doping of the emitter, any, or you increase the thickness of the emitter, right? So these are the two things. Other things you cannot change. You cannot change the emitter area, right? Emitter area will define the current, right? Anyway, if you need high current from the transistor, you have to increase the area, right? dp is related to NE, right? If you increase NE, then your dp will change, right? Okay, so these are the three things, right? So so what I have to do for IP to be low, I have to increase my NE, I have to increase my T, right? So these are the two things. These are the, if you are device designer, you have only two, you have only these two options, right? So what is generally done is you could increase NE. That's the reason. That's the only reason to increase the emitter injection efficiency. Your emitter is highly doped, right? So in your bipolar transistor, your emitter is highly doped, right? Emitter is highly doped. You could emitter is highly doped because it's highly doped just to decrease your, I mean, just to decrease your IP, just to increase the injection efficiency, right? Right. So this is very easy. You could highly dope the emitter. Another thing is you could increase the emitter thickness, right? So increasing the emitter thickness is not very easy in case of normal bipolar transistor, but if you go to heterojunction transistor, it is much, or the polysilicon emitter, or the single polysilicon or double polysilicon. We'll discuss those things. Why this is not easy in the traditional uh, bipolar transistors, right? So you have your N plus, this is your emitter, right? And as I told you, this is your base P, and this is your collector, right? Right, again N, right? So this is my thickness, thickness of the emitter, right? So, and I need a particular TB, right? If I increase the thickness of the emitter, what how I'll do? I'll implant. I'll make my high energy implanter using a high energy implantation. I could push N plus down, right? I could push N plus this area here. I could push it down to increase the thickness, right? The moment I push emitter very to a depth, right? How to, then it's very difficult to control the base width, right? Because base needs to be also implanted, right? So it is very difficult because because okay, so you want thicker emitter region, that means you have a high energy implantation. So let's say then if you have a base, because base comes below emitter, so the implantation energy should be much higher than the emitter implantation energy, right? So as you go on increasing this implanter energy, right, energy of the implanter, then it is very difficult to control the doping, right? So that is not traditionally done, right? So that's the reason uh, it's in a traditional transistor, your emitter thickness, by changing the emitter thickness is very difficult, because the moment you increase the implantation energy of the emitter implant, you have to increase the implantation energy of the base implant, because base is below emitter, right? And similarly, you have to increase the implantation energy of the collector, because collector is below base and emitter, right? So as you go on increasing the energy of the implanter, right? So it is very difficult to control the doping and control the depth. So it is not traditionally done, right? So what is done in the modern transistor is, so your emitter, what they do, your emitter is not a monosilicon emitter. What they do is you have a base, right? Your base, which is P, and your collector, which is N, and your emitter is mostly a polysilicon, right? So you could deposit polysilicon and dope it, right? This is a polysilicon, right? Uh, because you could dope this emitter, because so this is not defined, so this is done because this is done by deposition, right? So you could deposit silicon on top of your silicon, and when you do it by deposition, So you have a control, right? You could first, so what you do, you first define your base region, then you define your collector base region, then you could deposit whatever thickness you want, right, and you could dope it, right, because we have epitaxy process, because this is normally done by CBD, or you could also done by epitaxy. So during this deposition process also you could dope the emitter, right? So this is called the polysilicon emitter, right? So, and polysilicon emitter is very common in modern bipolar transistors, because once you have emitter defined by deposition, then you could easily control the thickness of the emitter, right? You could deposit how much, so you deposit 1 micron, you could deposit 2 micron, you could deposit 10 micron, right? So but it is very difficult to define by implantation, but it is easier to define by polysilicon emitter. So this is what people, this is what current modern transistors have, right? They have a polysilicon emitter, right? So that they could increase TE as per the design, and they could decrease IP and and increase the emitter injection efficiency. Okay, so this is about IEP. Any questions here? Okay, so this is about IEP. Another thing is, if you go to IBR, because I don't want your IBR, because your alpha T, your transport factor, right, depends on IBR, because your transport, your alpha T is ICN by IEN, and your ICN is nothing but IEN minus IBR, right? And because some are recombining, so right. So if you want your alpha T to be high, your transport factor, because once you, what you want, right, once the electrons are injected, so you want all the electrons to be collected, right? You don't want any electron to be recombined, right? So that's why your IBR, your transport factor can be increased, your alpha will increase, right? But how do you decrease IBR? So if you look at this equation here, so IBR can be increased by increasing NB. Means we want to decrease it. So decrease it means you could increase the base um, doping, or you could decrease the base doping, right? So basically there are two things. You could have to decrease the base width, or increase the base doping, or increase tau n, right? So these are the three things, right? So base doping means it's not very easy. Means we'll also discuss, because if you go on increasing the base doping, so it will have other problem, because you see how much the electron. So you see last thing, right? So the electron injected from emitter to base is VB by VT minus 1, right? This is the electrons injected, delta NE, right? Delta NB, right? So this is the electrons injected from emitter to base, right? Right. But if you go on increasing the NB just to decrease IBR, right? So what will happen? Your injection will reduce, right? Injection will reduce means your current will reduce, right? So if you see IEN may, your IEN, here you have NB, right? In the means in the denominator, right? So if your NB is increased, because it will help in reducing IBR, but it will not help, because it will also reduce IN, right? Overall current is reducing, right? So this is not the way you want to go. So NB is not actually touched just to, right? NB is not, right? So only thing is you could decrease the base width, or you increase the recombination lifetime. So this is very easy, because you could decrease the base width by proper device design, proper fabrication process. And tau n means this is the lifetime, and you have to make sure your base is defect free, right? If your base is defect free, then your tau n can be high. If your tau n is high, then there will no recombination. IBR will be anyway low, right? So the two way. So either you have to tau n. So these are the two things which is basically tried and basically used. So you decrease your base width, and you increase your lifetime by changing the changing the fabrication process. So to make sure that base do not have any defects, and while you make the base part very clean, right? So that your recombination lifetime is very high and your base current is slow. I think I should stop here today, but we could have discussion, right? All right, so let me stop here today, and we'll discuss this in the next class.